All right, so our next speaker is Dr. Virginia Smith. Dr. Virginia Smith recently graduated with her PhD from UC Berkeley and is currently a postdoctoral researcher in the computer science department at Stanford University, where she works on problems related to machine learning, optimization, and computer systems. All right.
Hey everyone, it's great to be back. I didn't leave that long ago. I graduated this August. So I've been a postdoc in enemy territory at Stanford for the last 6 months. And I'll be there this year, and then next fall I'm starting as an assistant professor at Carnegie Mellon University. So today I'm going to be talking about some of my research, which is centered around developing machine learning methods and theory that are more tailored to modern computing systems. So the motivation for this work comes from the fact that the way that we think about solving machine learning problems in practice is starting to change. So what does this workflow typically look like? You start with your data set and a problem that you like to solve. So for example, let's say that you'd like to identify high-quality news articles. So this is actually not a randomly selected problem. I worked with Isabel Stanton on this problem when I took a brief internship at Google. So she's also a Wixley alum, and you'll hear more from her later today. But once you have this problem and you have a data set and you know what problem you'd like to solve, the next sort of major milestone is selecting the machine learning model to solve that problem. So this could be something like deep learning or an SVM or logistic regression. Under the hood, in order to actually fit that model to your data, you often have to solve an optimization problem. And this is because many of these models can be posed as trying to find the optimal model W that minimizes some function over your data. What's missing in this workflow, however, is that in modern problems, in practice, when we're dealing with large data sets, there's a crucial component missing to this workflow, which is what sort of system setting you're in. And that system and the properties of that system can have a major impact on the optimization algorithm that you select to fit your model to your data. So this is sort of a cartoon drawing of data distributed over multiple machines, but what you should really be imagining is something like this. So a massive data center processing lots of data. And this is a problem that I looked at tackling during my thesis work at Berkeley, which is thinking about how to perform distributed optimization very quickly over these large distributed data centers. Some of this work went into developing a framework called Coco, which has been implemented in various frameworks like Flink and Spark, and has also become the default linear solver in TensorFlow. But more and more recently, data is not necessarily coming nicely packaged to you within a data center. So some problems that I've been looking at recently consider what happens when we go beyond the data center. Data here can be generated from things like mobile phones or sensor networks or wearable devices, and these networks now can be distributed across the country or across the globe. And they present a number of new difficult challenges in thinking about how we solve this problem. So in particular, whereas in the data center environment, you might have hundreds to thousands of machines, here you might have millions of devices in your network. Whereas in the data center, you might have all of your machines being the same machine. Here you might have very different devices in the network. You could have someone with a very new phone or someone with a very old phone or a phone that's not connected to internet. So you can have a ton of issues with heterogeneity on the system side. There can also be heterogeneity in terms of the actual data that's generated. So you could have very unbalanced data or data that's coming from non-identically distributed distributions. So much so that there could be interesting underlying structure to the data that's being generated. And so in terms of thinking about this problem beyond the data center, these challenges sort of break down into the more systems-related challenges as well as the statistical challenges. And in solving this problem, sort of the 1-second summary of this work is that beyond the data center, the system setting plays an impact not only on the optimization algorithm, but also on the machine learning model that we select to fit to our data. So the system setting is basically tightly coupled with this entire machine learning workflow. So I'm going to talk briefly about some recent work trying to tackle these two challenges beyond the data center. In terms of tackling the statistical component, so the goal again is that you'd like to be able to fit a model to data that's distributed across these various devices. So imagine that each of these gray circles is a device, and they're different sizes because they're generating different amounts of data. One way to fit a model to this data would be to assume that it's all coming from the same distribution and to fit one single model across all of the data. However, what you're ignoring here is that there might be some interesting structure amongst this data. And just because we're both generating data doesn't mean that it should be coming from the same distribution or we should have the same model. On the other extreme, we could each have our own models. So we could completely ignore information on the other devices. But this ignores relevant information that might be useful in improving my own model. So what we propose is something in between. So we have global models that learn the structure across the different devices. And this is something that can be naturally captured through a multitask learning framework. So in the multitask learning framework, you're still learning via these losses separate models, one for each device. But now you're imposing some structure across those models through something called the task relationship matrix. And so the multitask learning setup, this framework is extremely general. So you can capture a lot of interesting different relationships amongst the tasks in the network. Things like them all being related, or there being outliers, or clusters, or groups, or asymmetric relationships where you might have a power user in the network. So what we've seen is that by using this multitask learning setup, we can significantly improve the accuracy and the performance of the machine learning model on real federated data sets that are generated across these massive networks of distributed devices. But the challenge then becomes, how do we actually solve this model with all of this federated data? And so the challenge is thinking about how to solve this multitask learning objective, given that all of the data is distributed across the devices in this massive network. So in terms of the concrete challenges, certainly in comparison to the data center setting, communication can be extremely expensive here. There are also significant challenges related to the fact that there is heterogeneity both in terms of the statistics and the systems. And this can cause massive issues with stragglers and fault tolerance. And so since this is a short talk, I'll just give you the high-level summary. The main idea that we've taken in approaching this work is to take a communication-efficient method that works well in the data center setting and to modify it to handle these specific challenges of this federated setting beyond the data center. So specifically, we modify it to handle multitask learning, stragglers, and fault tolerance. And this is something that we're doing both in the method and in the theoretical convergence rates that we've developed for the method. So I'll give one quick example of some of the results that we've been seeing. So again, this is for real federated data sets that have been distributed across these massive networks. And what you can see is that the method that we've developed called MoCA, which is shown here in blue, is able to converge much more quickly than the other state-of-the-art solvers for a system like this. And in fact, it's converging by 2 orders of magnitude, so more than 100x faster than the other methods. So what you can see is that by thinking about how the system interplays with both the optimization and the machine learning model, we can improve both the accuracy and the convergence guarantees of these methods for real practical workloads. So with that, I'd be happy to answer any questions. Thanks. Thank you.